So in this lecture, we'll see about the Huffman coding. So what is meant by Huffman coding? It is basically a lossless data compression technique that is used to reduce the number of bits needed to represent the data. It assigns shorter, what it will do is nothing but it will reduce the number of bits that is needed to transfer or represent the data. It also assigns shorter binary codes to more frequent characteristics and longer codes for less frequent characteristics. Okay, so this is how we are doing the Huffman coding, and this is why we are doing the Huffman coding. So the Huffman coding we can explain you with an example. Okay, so now in the Huffman coding, so I'm going to give a simple. So I'm having the symbols. Okay, symbols as A0, A1, A2, A3 and A4. Okay, and the probability of occurring each so the probability of occurring each pixel is given by 0.4, 0.2, again 0.2, 0.1, 0.1. Okay, so these are my simples and these are the probability of occurring. So if an image I'm taking, so these are the pixels and these are the probability of occurring the particular pixels. Okay, so now we'll start doing the Huffman coding. So in this, what I have to do is nothing but I have to write the symbols or the pixels in the descending order. Okay, so already in the question itself it is given in the descending order, so I can write it as such. So it is given by like 0.4, again 0.2, 0.2, 0.1, 0.1. So for example, if the probability of occurring A1 is coming as 0.4 means what? I have to write, and A0 is 0.2 means I have to write again 0.4 first, then 0.2, 0.2. Okay, so like that it should be in the descending order. Okay, so now we'll start the Huffman coding. So in this, what I have to do is I have to add the last two probabilities. Okay, so I have to add the last two probabilities. The last two probabilities here it is getting 0.1 and 0.1. So when I'm adding 0.1 and 0.1, I'm getting what? 0.2, right? So I'm just adding it here. 0.2, and I have to add all other pixels as such. Okay, right. So next what I have to do is nothing but I have to again add the last two pixels. Okay, so here what I'm doing 0.4 plus 0.2 plus 0.2, what I'm getting 0.4, right? Again when I'm adding and writing, I have to make sure it should be also in the ascending order. Okay, so I can write as descending order, 0.4, then this 0.2 plus 0.2, what I'm getting again 0.4, and this 0.2 I have to write it afterwards. Okay, I should not write whatever I'm getting, I should always write in the descending order. Next what I'm doing, I have to add these two pixels, okay, these two probabilities, and these two probabilities, when I'm adding 0.2 plus 0.4, I'm getting what? 0.6. And I'm writing this probability as such. Understood? So for your understanding, I'm just writing these two things added. I got here this thing, and these two things added. I got this one 0.4, and these two things added. I got this one. Okay, understood. So now, next what I'm going to do is, I'm just going to take another color pen so that it will be easy for you to understand. So now I'm going to mark an initial probability. Okay, so I'm going to mark an initial probability. So I'm going to mark this initial probability. Here it is 0 and here it is 1. Okay, so better I take the red black pen. Okay, so the initial probability, here it is 0 and here it is 1. This is, I'm just assuming this initial probabilities. Okay, now what I have to do, so for I'm just the same thing, I have to do it for all the last two probabilities. 0, 1, here also 0, 1, here also 0, 1, right? Now, so the 0.60, so 0 I'm getting by adding 0.4 and 0.2, right? So this probability I'm going to give here. So 0 I'm going to give here, and the 0 I'm going to here, because I'm getting 0.6 by adding these two, right? So that I have to give here, and 0.4 I have to, the same thing that I have to give here. Now this 0.4 I'm getting by adding 0.2 and 0.2, right? So now this 0, 0 for 0.4 I have to give over here. Okay, and this 0, 0. And the 0.2 is again the same thing what I'm getting. So 1, 0 and 0.4 is 1. And next to the 0.2 I'm getting by adding 0.1 and 0.2. So that is nothing but 1, 0, 0, right? 1, 0, 0, 1, 0, 0. So this 0.2 is 0, 0, 0. Here it is 1, 0, and here it is 1. So this is what we are doing. It is assigning binary codes to the more frequent characteristics. Okay, we're just giving shorter binary codes to the more frequent characteristics and longer like binary codes to the less frequent characteristics. This is what the meaning. And now, so in the, like, I have to find, so in this, if I'm doing only a code, I won't be able to understand. So this code is only used for transferring only, so, right? So in order to give a sufficient information about the data compression, I have to find some kind of matrices. So first one in that matrices is nothing but the length of the code. Okay, so the length of the code. So the length of the code. So the length of the code, Li, so the equation. Okay, so this is my first matrix I want to calculate. So that is given by sigma I equal to 1 to n pi into L. Okay, pi into L. So that is nothing but that is equal to what is first probability? 0.4, right? 0.4. And what is the number of sorry, so So what is the number of pixels I got? So what is the number of pixels I got for 0.4? It is 1, right? So into 1. So similarly for 0.2 the number of pixels is 2. Okay, and similarly plus for 0.2 again the number of pixels is 3. Okay, plus again 0.1 the number of pixels is 4, plus again 0.1 the number of pixels is 4. So this is what we got here. So 0.4, 1, 0.2, 2 bits, and 0.2, 3 bits, 0.1, again 4 bits, 0.1, 4 bits. So when I'm doing all those things, I'll be getting, when you're doing the calculation, I'll be getting the length of the code that is equal to 2.2. Okay, 2.2. So next thing I want to find is, next matrices for the image compression is nothing but the entropy. So entropy is given by mu. Okay, so that is equal to the equation sigma I equal to 1 to n pi, the probability, into multiplied by log log 2 to the base 1 by pi. Okay, so when we are expanding this, how we can write? So that is equal to first probability is 0.4 log 2 1 by 0.4, okay, plus etc. The last probability is 0.1. 0.1 log 2 1 by 0.1. Okay, so you have to do the log 2. So in the calculator, so log 2, how we are going to do something like log of the particular value divided by log of 2. Okay, so like that, if you're doing, you can you can get the log 2, or else you can do that in the settings in the calculator and you can do. So if you're getting this, you'll be getting your entropy is around 2.1. Okay, 1, 2 something. Okay, now you have to find the efficiency. Next matrices. So the efficiency, is given by eta. So that is equal to mu divided by the total length. Okay, so that is nothing but the mu is 2.12 divided by the total length is 2.2. So you will be getting approximately around 0.96 or approximately 96%. Okay, it's a right good amount of percentage. And next one is nothing but your redundancy. So the redundancy, so that is given by R, so that is equal to 1 minus efficiency, right? Redundancy is always 1 minus efficiency, 1 minus eta or 1 minus efficiency. So that is around 1 minus 0.96. So that is around 0.04. So that is equal to what? Is equal to 4%. Okay, so this is how we have to do the Huffman coding. Okay, so the Huffman coding, if you are given any kind of images with the probability, you have to find the number of bits for each and every pixels, and after you find it, you can find the coding matrices. Okay, so you can find the length of the code, entropy, efficiency. So all those things you can do it. So that these are the things that will be confirming that your compression you have done is better. Okay, so I hope you understood the Huffman coding. Thank you.